Hydrate. Hydrate. When you hydrate something, what do? Okay, in general terms, when somebody says you're going to hydrate something, that means you're going to add water to it. Okay, some compounds are hydrates. They have water added to them. Okay, so a hydrate is an ionic compound that when it makes the crystal, it grabs water molecules along the way. When it makes the crystal, it grabs water molecules. So as part of its pattern of alternating charges, water can hang on to some of those charges to make the crystal more stable because oxygen's got a negative piece that can hang on to the positive ion and positive end that can hang on to the negative ion, so it can help stabilize that crystal. Okay? So when it turns from something dissolved, you let the water evaporate and turns into a crystal, it grabs some of the water along the way, making that crystal. Okay with the process we're talking about here? So you've got it all dissolved, you let the water evaporate, all the solids form. It's going to make water part of its crystal. That's a hydrate. Okay? Now, it's not going to be a random number because it's a crystal. Regular repeating pattern. So every time you build it, you have to use the same number of water molecules. If you're going to make that crystal, you got to use the same number of water molecules every time. Otherwise, it can't be a regular repeating pattern. Because if it was a different number of water molecules, it wouldn't be regular and it wouldn't be repeating. Okay. So we can specify how many water molecules it is. So when we write the name, we specify that by write the formula. We write the formula, then we put a dot right in the middle, and then we write down how many water molecules. It's harder to explain than it is to do. COCl2 dot 6H2O. We saw one of those on the homework along the way, where it asked you how many waters there were. Okay. So what they're saying is, when cobalt chloride makes its pattern, in making the pattern, for every cobalt you use 6 waters. For every chlorine you use 3 waters. Because there's 2 chlorines and 6 waters. Right? Well, why can't you use so many more waters? Well, think about it. Cobalt's going to be a much bigger atom. Those small water molecules can surround it and help stabilize it. Chlorine's going to be a big atom. Those water molecules can surround it. So if you've got 2 big atoms, you can put small water molecules in between in the pattern. Okay. So now we have to write the name of that. To write the name of it, all we do is add a third word. And that third word, we put the prefix that means the number, and then hydrate to tell us it's water. So first, I'd have to name COCl2. So CO is a metal. It's a transition metal, so it needs Roman numerals. So it's cobalt something chloride. Chloride's 1-. There's 2 of them, so that's going to be cobalt 2 chloride. That part doesn't change. COCl2 is cobalt 2 chloride. Now I need to say 6 waters. The prefix for 6, the same list as we use for molecular. Hex. Right? 2 for 6 is hexa. So this would be cobalt 2 chloride hexahydrate. So those prefixes we learned for molecular compounds get used here just as well. And this time we won't have to worry about double vowels because the second word is always going to be hydrate. So we get to use the whole prefix. Look real complicated? Okay, let's just try a couple, just make sure we're doing it. BaCl2.2 H2O. So the first half is just like every other name we wrote. Ba is a metal. It's ionic. BA's barium doesn't need Roman numerals. It's represent a particle, so it does not need Roman numerals. So that would be barium. What chemists do with their mistakes. Okay. And then 2Cls is chloride, not dichloride because it's ionic. Ionic compounds don't get prefixes. It's easy to figure out there's got to be 2 chlorines because Ba is always 2 plus. Then we have to say 2 waters. Dihydrate. Really complicated? Nope. Pretty straightforward. I like the simple systems that are just, okay, I've got barium chloride and 2 waters. Okay. Okay, Mg is a metal. Not a transition metal representative. It's a group 2A. So I don't need Roman numerals. So that's magnesium. OH, polyatomic ion, hydroxide. Five waters. 5 is penta. So that would be pentahydrate. Incredibly complicated? Well, hopefully it won't be too much when we go the other way without any instructions. Sodium carbonate decahydrate. Second word is not active. Second word doesn't have a prefix. It's ionic. Okay? So I have to worry about charges. Sodium is a metal. It's got a 1 plus charge. Carbonate, ATE, polyatomic ion, CO3 with a 2 minus charge. So it's Na2CO3. And decahydrate. Deca is 10. So 10 H2O. So give us lots of these on the test, Mr. Green. Yeah, because you're not going to make a mistake on the hydrate part. Where you make a mistake is forgetting to put charges in. It didn't say 2 sodiums. Calcium sulfate dihydrate. Calcium, 2 plus. Sulfate, SO4 with that 2 minus charge. So CaSO4 is right. And di is 2 hydrate. My favorite chemical. It paid for college for me. I worked at a quarry. The quarry I worked at was a gypsum quarry. Gypsum is calcium sulfate dihydrate. Okay, it's the mineral form, but what you dig out of the ground is calcium sulfate dihydrate. Okay? And what it gets used for, it's the stuff in drywall. Okay? Between the paper, you got that powdery white stuff. That powdery white stuff is gypsum. Talk about why they put it there in a little bit. And my job was to see how pure the gypsum was. That was my job. So this is the technique we use to do that. We took samples of rock because we were shipping, 20, 50, 60 tons at a time. Oh, no, sorry. No. 11,000, 12,000 tons at a time. Boatloads. We were loading boats with rock. They would take those boatloads of rock to Detroit or Chicago, where there was a drywall factory. Okay? What they need to know is how pure it was, and the way we did it was we just took the sample, ground it up, weighed it, then put it in the oven and cooked it for 2 hours. When you cook it, the water leaves. That means the crystal falls apart, turns into incredibly fine white powder. Okay? And by how much water it lost, we could tell how pure the rock was. Because there's a certain percentage that is pure calcium. There's a certain percentage if it's pure. And how close we came to that would tell us how much pure rock we had. Because we guarantee our customers 95%. The rock would be 95% gypsum. So we tested it every 600 tons to make sure that we stayed within those guidelines. Okay? That was my job, baking rock. Okay? So what was I shooting for? What was I looking for? Percent water in calcium sulfate dihydrate. What is the percent water? Which means that I want to find the percent water. That's going to be the grams of water over the grams total times 100%. Everybody see how I translated that? Percent, it's just a regular percentage. My part over the whole thing times 100%. I can pick any amount of calcium sulfate because the percentage should stay the same. I am going to pick 1 mole. Why do I pick 1 mole? Because then I know all the numbers I need. Okay. In 1 mole, I would have 1 Ca, 1 mole of S, 4 moles of O, and 2 moles of H2O. I'm not going to do 6 O's and 4 H's. I want them separate because I want to know grams of H2O. So I should figure out grams of H2O along the way. See why I want to do that? I want that number up there. Okay, so 1 Ca is 40.08 grams. 1 S is 32.07 grams. 4 oxygens is 64.0 grams. And water is 2.02 and 16. So that's 18.02, which is, so 2 of them would be 36.04 grams. Everybody okay with where I got 36.04? 2.02 for hydrogen, 16 for oxygen, H2O is 18.02. I have 2 waters. So 2 times 18.02 is 36.04. Okay? And the total for that, when you add up all those numbers, 40.08 plus 32.07 plus 64 plus 36.04 gets me 172.19. And that's the numbers look, there's the numbers I need for my percent. Those 2 numbers. 36.04 grams of water out of 172.19 grams. And that works out to be 20.93%. 4 sig figs on my 36.04. 5 on my 172.19. So it's just like finding percent composition, except you don't count H's and O's separately. You do it all at once. If I'd asked you to find percent calcium, you would put grams of calcium over the total, right? Well, I just put grams of water over the total instead. So it's actually no new math. Okay? So why do they use gypsum? Why do they make walls out of gypsum? Well, because they're there for fire protection. Because what's going to happen when fire comes up against a wall and the wall is made out of gypsum? It's going to heat that gypsum and the gypsum is going to give off water. Is that going to make the fire spread? No. And then once you get rid of all the water, then you got to heat rock. Is the rock going to burn? Rock doesn't burn. Okay? So the reason why they do it, it's fire protection. If you heat it, first thing it does is give off water, which tends to cool it off and get rid of the fire. Okay? And where it came from was up and through the late 1800s, when there was a fire in town, there was a good chance you were going to burn down the whole town because everything was made of wood. All your walls were wood, your roof was wood, everything was wood. So when one part started burning, if there was any wind, all your neighbors burned down too. And the stories about London burning down 3 or 4 times. Chicago burned down in the late 1800s. And they said, oh, no, we need to rebuild the city. We want to rebuild it in a way that it doesn't burn down again. So they were the ones who instituted that you had to put, back then it wasn't gypsum, didn't have the finished product, but you had to put plaster on the walls. Because plaster is gypsum. Okay? Fact is, there's another kind of what you can do. What plaster ends up being is calcium sulfate hemihydrate. Hemihydrate, half a water molecule. Okay? And we go to store to buy it. It's called plaster or plaster of Paris. Okay? And this is the stuff that all you do is you got a powder. Where I used it in Boy Scouts was with animal tracks. To make a cast of an animal track, you mix plaster of Paris with water and you pour it into it. And that plaster of Paris, it's going to turn into the dihydrate. It's going to pick up those extra water molecules, which means it has to make a new crystal. And when it makes a new crystal, it's going to make a solid in the shape of whatever it's sitting in. That's how you get a plaster cast. This is how cement and concrete works. Up in Apple Valley, there's a big cement plant. Well, they take a rock and heat it. It drives off the water. Okay? The water goes away. That is cement. They pour the cement together with gravel and sand and then add water. When that water gets added, the water hydrates the one that they dehydrated. It makes a new crystal. That new crystal forms around every grain of sand and every rock. And that's cement. But most of it is cement and rock with new crystals forming around it to keep everything together. So that's where hydrates show up in your life. It's commonplace. Cement, drywall, those places. Any place you add water and stuff gets hard. So we just took a formula and figured out a percent water. That means if I have a percent water, I should be able to figure out the formula. Hopefully you're used to working every problem backwards, right? We do it one way, and then we do it the other. Okay, so first, zinc nitrate. Zinc. It's a transition metal. How the heck am I supposed to know the charge of zinc? Because we've memorized it. Zinc is on our list as always 2+. A couple ways to remember that is, I cross my Z's so they don't look like 2's. And the reason why it's 2+ is zinc is S2D10. It loses the S2. And it has 3D10 full. So it's got its whole third energy level full by losing just those 2 electrons. That's why it loses 2. Because then it ends up with full orbitals, low energy. Nitrate, nitrogen and some oxygen, that's from nitrate. Now I just have to remember that it was 3 oxygens and a -1 charge. So the zinc nitrate part is ZnNO3 2 dot something H2O. We need to fill in that number. So that number is going to be a ratio. How many water molecules there are for each zinc nitrate? And if it's true in molecules, it's true in moles. So what I'm looking for is moles of water over moles of zinc nitrate. That will tell me how many moles of water for each zinc nitrate. That means I got to get moles of water and moles of zinc nitrate. How the heck am I going to do that? Well, I must be using that 43% water. I can pick any amount. I'm going to pick 100 grams. Why do I pick 100 grams? Because then I know I've got 43.3 grams of water. And actually, notice the fancy math here, 56.7 grams of zinc nitrate. It's got to add up to 100. If 43.3 grams is water, the rest has to be zinc nitrate. Make sense? So by telling me the water, they were also telling me zinc nitrate. I needed two numbers, they gave me two numbers. Okay, now I just have to change those grams to moles. Grams of H2O to moles of H2O. And we just said 1 mole was 18.02 grams. So 43.3 divided by 18.02. And that is 2.40 moles of water. And zinc nitrate, grams of zinc nitrate, 2 moles of zinc nitrate. 1 mole is, zinc is 65 point, did you say 39? Yeah, there's a few places where our periodic tables differ. 65.39 plus 2 nitrogens, 28.02, plus 6 oxygens. This time it is 96. I admit my mistakes. I learned from them too. So I got 189.41. 65.39 plus 28.02 plus 96. 189.41. That can't be 189.41. What's it doing? I mean, I'm looking at what I typed in my calculator. 65.39 plus 28.02. 28.02. 2 n's. 28.02. So it is 189.4. Yeah, 189.41. So that is 56.7 divided by that answer gets me 0.299 moles of zinc nitrate. So that is, now I can go back up here and that's 2.40 moles of water over 0.299 moles of zinc nitrate. And my calculator gives me 8.02, which is 8. Right, so there's 8 waters for every zinc nitrate. So the number's 8. This is just like using percent composition and going backwards. Okay? So this is what we're going to do tomorrow. I'm going to give you a hydrate. You're going to heat it and get rid of the water. By how much water you lose, you'll be able to figure out that number. It's as close as we can get to an empirical formula for you. It's something that's a little challenging. All the other empirical formulas I can do where you know the answer before you start and it doesn't do you any good. But here, don't know the answer before you start. You figure out how many water molecules there are for each one. So that means we have to heat stuff tomorrow. And we have to heat rock. And I don't think our hot plates are hot enough to do it. So tomorrow,